Good evening, everyone. I'm Marcia McNutt. I'm the president of the American Geophysical Union, and I have the honor this evening of introducing to you Dr. Ross Stein, who will be presenting the 2001 Frontiers of Geophysics lecture for the American Geophysical Union. Ross grew up in Los Angeles and then bounced back and forth between the coasts for a number of years. He was an undergraduate at Brown University, did his PhD at Stanford, then went back to the East Coast to become a postdoc at Columbia, and he has worked now for the last number of years for the USGS. And I think everyone in this room probably understands what USGS stands for. Unplug some government scientists. Ross is stationed at the Menlo Park office of the USGS, and I believe all that means it's the place where his email never arrives, because Ross himself actually is not very often there. I usually run into Ross in France or in Woods Hole, and of course lately he spent a lot of time in Turkey. Ross this evening is going to give us, I think, a very engaging view of the possibilities of looking at probabilistic earthquake occurrence using stress as an understanding for why earthquakes are clustered in time. So without further ado, Dr. Ross Stein.
I love Marcia. And beyond that, I'm very appreciative of this opportunity to speak with so many of my colleagues about something important to us. Now, to warm up, let's play a game. Let's forecast the probability of a magnitude 6 earthquake occurring in Southern California during a one-day period. Or better yet, let's make it within a 100 by 100 kilometer box in Southern California. Okay? Your turn. What are you going to do? Well, my guess is you're going to go to the catalog and you're going to discover that there have been 40 magnitude 6 and larger earthquakes in Southern California during the last century. So that's a rate of 0.4 per year. Now we divide that by 365 and we get a daily rate of about 1 in 1,000. Since it's a small number, the rate is the same as the probability, 1 in 1,000. Now if we further realize that a 100 by 100 kilometer box is about 3% of Southern California, we divide by 30. And you get for your answer 1 in 30,000 is the chance of that 6 or larger earthquake occurring in any one day in a 100 kilometer box in Southern California. Okay, you happy with your answer? Now it's my turn. Now I'm going to pick a particular day, the 24 hours following the Landers earthquake in 1992. And I'm going to pick a particular box, the 100 kilometer box centered on the main shock. And you say, hey, wait a minute. My game, my rules. You just didn't know about those rules. So I go to the statistical catalog too. I go to the statistics compiled by Paul Riesenberg and Lucy Jones in several papers in Science the last decade and find out that the probability of a magnitude 6 or larger earthquake during the day after a magnitude 7.3 event within 100 kilometers is 0.65. So you're at 1 over 30,000 and I'm at 2 over 3. So I've got a number that's 20,000 times higher than you. And you say, hey, wait a minute. That's an aftershock. That's not fair. If you skim off the aftershocks, what's left over in the catalog is random, and your number is a good number. Well, it so happens that there was a magnitude 6.5 just 3.5 hours after Landers, but it wasn't on the fault rupture. It was 40 kilometers away. Aftershock or no? I don't think we know if it's an aftershock or not, but what's important is that if I give you the Southern California catalog, by someone's definition, a third to a half of the earthquakes in that catalog are aftershocks, are contingent events, events contingent on another. And if I hand you the global catalog, which is larger earthquakes, magnitude 5 and larger, something like a third of the earthquakes in that catalog too are aftershocks. So why are we throwing away the part of the catalog which seems most predictable? And speaking of predictability, hasn't my case fulfilled the canonical requirements for an earthquake prediction? Time, 24 hours, magnitude 6 or larger, a damaging earthquake, and place within a 100 by 100 kilometer box. And you say, wait a minute. this doesn't fly because we all know that earthquake prediction, and we've all learned through 20 years of hard labor here that earthquake prediction doesn't work, and it doesn't work for a simple reason, which is that any tiny earthquake has some probability of cascading into something larger. And then there's a yet diminishing probability that that somewhat larger earthquake will cascade into something larger still. And there's nothing that tags that little earthquake that it has a large future. But I say that cannot be right. If I can pick a time and a place where the chance of that earthquake cascading into a larger one is 20,000 times higher than the background, that's an inadequate description of the process. What we need to do is to understand why some part of the catalog does seem to be so predictable and build that into our thinking of how earthquakes occur. So the central argument of this talk is that if you increase the stress toward failure on a fault in the earth, no matter where it is, you will get a sudden increase in the rate of earthquakes on that fault. And that will decay back towards its previous rate over time. And the corollary is, if you suddenly drop the stress on a fault, then the rate of earthquakes will plummet on that fault, and that will slowly recover back towards where it came after some period of time. So the first case is what we call aftershocks, and the second case, for lack of another word, we might call antishocks. Now, I recognize that in trying to make this argument to you, you're entitled to legitimate skepticism. And I'm giving you the benefit of the doubt here on the term legitimate. But so what I'm going to do is, while I try to make this argument, I will represent your point of view along the way and try to raise the objections that are presented by this work. So essentially, I'll advocate, you'll annihilate, and we'll see where we end up. Now, because this is a frontiers talk, I'd like to speak to where we might be headed as a community. But because it's a union talk, I'd like to speak in plain English. So the pledge I'm going to make is, if you stay with me, you will understand everything that I tell you. And so now we can start with the slides. Where should we start? The strongest argument that earthquakes are not a random process in which we're simply throwing darts at a fault line is in Turkey. And so that's where I would like to start, along the North Anatolian Fault, where you can see a 1,000-kilometer-long feature which suffered a falling domino sequence of earthquakes between 1939 and 1999. Now, the bottom is the map of the fault, and on top I'm going to plot the rupture area for each successive earthquake. The vertical axis is the slip, the horizontal axis is the length along the fault, so the larger the blob of color, the larger the earthquake. So I want you to watch this process take place. 1939, 42, 43, 44, 51. I want you to see that earthquakes are generally occurring just a few years apart. You can obviously tell that it's generally propagating to the west, but not exclusively. That earthquakes tend to abut, except for when the fault is what we call en echelon, where we have side-by-side pieces of fault. And that when the 60-year period is done, there's only about 10% of the fault left unruptured. Now, the first argument I want to make is that since the average slip of these earthquakes are about 4 to 5 meters, and the fault is known to have a slip rate almost identical to the San Andreas, about 22 or 4 millimeters per year, the average time between these large shocks needs to be about 200 to 250 years. So if we're going to look at 60 years, which is just a quarter of that, we should see about a quarter of this fault light up in earthquakes. And instead, we see almost the entire fault. So that alone should tell us this is not a random occurrence. These earthquakes are interacting in some sense. But further, we can see this tendency for earthquakes to abut, unless the fault is en echelon. We can see them tending to occur very rapidly in time, a few years apart, but we also see waits as long as 30 years or even 60 years. All of that we need to hardwire into some notion of how earthquakes behave probabilistically. So let me show you how we think about this. We're going to the end of the rupture, the site of the 1999 earthquake, which was centered on Izmit, and I'm going to bring up the North Anatolian Fault here. The rupture occurred in the middle of that. I'm going to put a fence across the fault, simplify the fault with a straight line, and fly overhead. And now you can see that the fence, which is made up of squares, is being sheared into right lateral parallelograms. In other words, the other side appears to be moving to the right. When the stress overcomes the frictional resistance on the fault slips, and all of that right lateral shear is removed from the system, and we have now released the stress along the fault. And this is H.F. Reed's elastic rebound hypothesis. Okay, so far so good. The stress is built up on the fault during the several hundred years between earthquakes, drops on the fault during the earthquake. But what happens beyond the ends of the fault, here and here? Does the stress also build up and drop, or does it undergo a different evolution? So let's look at this picture again, but this time, rather than putting a fence across the fault, I'll put a grid of points so we can see what happens beyond the end. Again, I'm going to simplify the fault with a straight line. We're going to fly overhead, densify the grid, and watch stress accumulate. And the rupture again, which turns blue, is in the middle. I want you kind of to focus on what happens beyond the end of the fault, some of these boxes here. And so when the earthquake occurs, what you see is the shear that's now being built in, the stress that's being built into this fault zone, rises. Look at how that is being further deformed in a right lateral sense. Now, if we color the right laterally sheared parallelograms red and the left laterally sheared boxes blue, you can see that while we've dropped the stress along the fault, we've increased it beyond the ends. So this one, which we started with, our offset fence, that could be an offset road, we've brought stress beyond the ends. Now, we can also think in terms of how failure is promoted by unclamping the fault, and failure is inhibited by clamping it shut. So where we've squeezed these wire frames down, we've clamped it. Where we've pulled them apart, we've unclamped it. So if we had an en-echelon fault here, it would be brought closer to failure, and if it were here, it would be brought farther from failure. Now, these two components of the Coulomb stress function can be added together. Here's the first one you saw. That's the shear stress change. An earthquake here has increased it here and here, and to a lesser extent out here. And here's where we've either unclamped the fault or clamped it. Now we simply multiply the middle frame times the friction. For a Teflon fault, that would be 0. For a very rough, jagged fault, that might be 1. And then we add them together to get the Coulomb criteria, which says if we just had a rupture here, we've increased the stress toward failure here, and to a lesser extent here, and we've inhibited failure here. Now that is the theory that underlies this work. So if that made sense to you, we're going places together. And the place I want to start is going back to the North Anatolian Fault, but let's start simply with just a straight fault. And I'm going to put each earthquake on with its correct length, but I'm going to give them all the same slip, so the pattern is simple to see. So here's the first one in 39. Notice how it increases the stress beyond the end, which promotes the next one, etc. And if for whatever reason I put a nail through the fault here, the fault won't move, but you can see stress is still transmitted beyond that point. You can also see why, if there's some reason, unknown reason, why the fault doesn't rupture this way, it will tend to rupture in the other direction, because we still have that blowtorch in front of the fault, and behind it is just a growing area of blue. So after this 60-year sequence of earthquakes, almost the entire fault has turned blue. The stress has dropped, the hazard has dropped, except at the ends. Now let's do this again, but this time we'll use the true shape of the fault, and we'll use the slip that Aykut Barkut developed from observations of the surface rupture. Now I want you to start looking here. This is where the 1942 earthquake is going to rupture, this en-echelon fault. Look what happens to the stress just before it ruptures. See how that was yellow? There's a very low area of stress out here, there's stress here, and eventually, even though this is blocked, you can see stress is transmitted. It's going to go right around that corner there, 1957, 67, and finally the site of the 1999 earthquake at Izmit, the first one, which occurs here and loads this part of the fault, and then we have the November shock. And again, if you kind of blur your eyes, you'll see most of this map has turned blue as a result of the stress transferred by all of these earthquakes. Now, because this is where the population is, this is where we need to take a good look. So I want to bring us a little closer up and show you that same pattern of stress just before the Izmit earthquake occurred in 1999. And here we have a good enough seismic catalog to superimpose the small earthquakes, the little pops on the records that are occurring in the background, these little juju beads here. And what I want you to see is that the background seismicity tends to locate in places where we calculate the stress to have risen. And it tends to be absent in places where we calculate the stress to have dropped. So that provides some kind of additional validation, which is useful considering we're dealing with a small number of large earthquakes otherwise. And if this is so, then we would expect to see the same phenomenon with the aftershocks of the Izmit earthquake, which are shown here. And what I want to emphasize is that the rupture extends between here, and off the rupture, where we calculate the stress to have risen, we see aftershocks occurring, and in fact, the November 12th magnitude 7.1 earthquake occurred in this region where we calculate the stress to have risen. And what's troubling to us is that earthquakes are occurring on the Princess Islands fault much closer to this population of 12 million people. So we're concerned that this fault has been loaded and is pointed like a gun toward the city. And that raises the issue of trying to translate some idea of stress to probability, so it's actually useful for people. And at this point I should tell you the dirty little secret, which is that 2 bars of stress, which are what you're looking at here, is what you put in your car tires. So we're not talking about something giant here. We're talking about what appear to be very small stresses having dramatic effects in the seismicity. So how do we translate stress into probability? We have a simple way of looking at things. Imagine you're out here at the future Doomsday rupture site, the November 12th rupture, and Izmit has just occurred here, and that's the simple version of that. Now out here, the stress was slowly rising with time. That's exactly the same as those squares slowly being sheared into parallelograms. Then the neighboring earthquake occurs and we have a sudden jump up. That's what you saw when suddenly it increased beyond the end of the fault. So we're going to move up to this failure envelope, wherever it is, earlier than we would have. And that's associated with you could think that we've advanced in time the occurrence of the earthquake, and that's associated with an increase in the probability of that earthquake occurring. For a long time, we thought that would explain the occurrence of falling domino sequences like Istanbul. But we were wrong, and we're wrong for a very simple reason. If the stress increase beyond the ends of the fault is rarely more than a few bars, and if the stressing rate on even fast faults, like the San Andreas or the North Anatolian fault, is not more than about 1/10 of a bar per year, this time advance is about 1 to 2 decades. Now recall that I mentioned that the inner event times for these large earthquakes are on the order of several hundred years, and there's a large uncertainty or a large variation on that, let's say 200 plus or minus 100 years. If you take numbers like that and you move them up by a decade or two, they'll be swallowed. You won't see anything. It won't cause successive earthquakes to occur. So that's not enough. And what we appeal instead is to the notion of rate and state friction developed by Jim Dietrich, which is that because the stress is suddenly applied as opposed to steadily, it dramatically increases the rate of earthquakes that occur and the probability. And this melts back or decays back over a period similar to an aftershock decay. This occurs because when the stress is suddenly increased, lots of sites for future nucleation show up and they're slowly expended. And as these sites are expended, the rate slowly decreases. Now, Dietrich and Ruin and others developed this with hunks of granite in the laboratory. So your legitimate skepticism is, well, okay, so you see it in the lab, do you actually see it in the earth? So let me try to argue that we do see it in the earth, and here's a site closer to home, Loma Prieta. Now the Loma Prieta rupture is right in this rectangle, and everything that you and I would call aftershocks are in about the yellow circle. We're going to forget about that and go well offshore to the San Gregorio Fault, where we calculate the stress to have risen by about a bar as a result of the Loma Prieta earthquake, and we're just plotting the earthquakes along that segment of the fault. And what you see is at the time of Loma Prieta, the rate of earthquakes climbs by well over an order of magnitude, and then slowly decays back over about 15 years. And this decay is exactly the decay we see in aftershocks, 1/T, which means that if we go 10 days out, the rate of aftershocks will be 1/10 it was 1 day out. If we go 100 days out, it'll be 1/100. So if I were to show just this plot to a seismologist, they would say, oh, that's an aftershock plot. But if you look over here, this is nobody's definition of aftershocks. And it says instead that this is a fundamental property of seismicity. If you suddenly increase the stress, you'll get a higher rate of earthquakes, for all magnitude bands, but this will decay back over some period of time. Now, your argument here will be, okay, maybe you see it, but you're seeing it for little tiny earthquakes. These are 1s and 2s and 3s, and we could care less about these earthquakes if we're interested in saying something about hazard. And that's a fair criticism, so let me show you that it actually applies to the North Anatolian sequence itself. Here, what I'm doing is stacking the times between each triggering earthquake and the subsequent rupturing earthquake. So let me give an example. The 1939 earthquake increased the stresses by more than half a bar at the site of the 1942 and 43 shocks just a few years later, but also the site of the 49 shock 10 years later, and even the 92 shock 60 years later. So if we plot this frequency, we'd have a higher number occurring in a few years, but we'd still be above the background rate for longer periods. We could do it again for the 43 shock, which triggered one in 44 a year later, and another one 8 years later. So we stack all of those, and we see that it's much more likely that you'll trigger an earthquake within a few years, but you're still above the background rate if you come out 40 or so years here. And in fact, this is a 1/T decay, just like an aftershock plot. So the things that we set out to build into the model, we can see here. We can see why the earthquakes tend to abut end on end, because we transfer the shear stress just beyond the fault. We can see why the en-echelon ruptures are occurring in a few places. That's where we've unclamped that neighboring fault. We can see why ruptures will tend to propagate in one direction. If for whatever reason the rupture won't go one way, it can get going in the other. We can see why it can go beyond this place. And so this is the notion of interaction. And now we want to just build that in to our traditional models of earthquake probability. What we generally assume is as those squares are sheared into parallelograms, in other words, the longer we get downstream from the last large earthquake on a fault, the more likely the next one. And that's represented here by the blue line. This is the renewal probability, gradually rising as we go downstream from the last earthquakes nearest Istanbul. We add to that the interaction probability that you just saw. And now you know why it has that shape and why it melts back toward the renewal over a long period of time. Now at this point you might say, well, okay, maybe there's something like that going on, but look, you're adding 12% to 50%, and when you deal with the true uncertainties on that interaction model, it's probably just dwarfed by the blue curve. So maybe what you're doing is just adding something somewhat uncertain to a larger, more important function, which is the renewal probability. Now, my answer to that is there's really nothing magic about a 30-year probability, which is what we're using here. And we use 30-year probabilities in California, of course, because Californians have only one source of money in their lives, and that's their home, and that we write a 30-year mortgage. We sign our names about 140 times. So 30 years is the longest period of time a Californian can conceive of. So that's what we use. But that has nothing, the Earth has no bearing on that. So if we look at a shorter probability period, such as a 10-year probability period, now the interaction almost doubles the probability because of this time-dependent decay. And if we look at a 1-year probability, it triples it. Now you might say, 1-year probability, who cares? Look how low the rates are. The 1-year probability just has, let's say, a 5% rate. It bumped from below 2 to 5. But if you're PG&E, our public utility here, that's not your thinking. Because like many companies, PG&E buys their earthquake insurance on the spot market every year. So if PG&E were unfortunate enough to be doing business in Istanbul, what we're saying is they should triple the amount of earthquake insurance that they're carrying. So our argument is these interaction effects are strong, but they're very time dependent. Okay, at this point, you might be saying, okay, well, maybe you can make sense of the North Anatolian sequence, but we all know that the North Anatolian sequence is rare. It's not something that we see everywhere. So it's a special case, not a general case. And beyond that, I had argued to you that if we increase the stress on a fault, we increase the seismicity rate. And if we decrease it, we decrease the rate. So while it's nice to see aftershocks in the red zones, what we really should see is seismicity rate increases in the red zones, and we should see seismicity rate decreases in the blue zones. So let's hunt for that. And the first place I'd like to look is at Northridge, the magnitude 6.7 earthquake. In black are its aftershocks, And in red is the calculation of the Coulomb stress change. And you can see that there's some accord between the distribution of aftershocks and stress, but what we're really interested in is the seismicity rate change, the rate after the earthquake compared to the rate before. And that's shown here on the right in the colors. So what's important is that these two patterns, right and left, are very similar. So it's the correlation between the two butterflies that's important here. And there's even a hint that where we expected to see a seismicity rate decrease, we might actually be seeing it here. It's just a hint, but there's something there. Now, at this point, your complaint might be, okay, maybe you can see it here, and incidentally, Paul Riesenberg and Bob Simpson have seen this for Loma Prieta, and Max Weiss and Stefan Weimer have seen it for Landers, and Shinji Toda and others have seen it for Kobe. You'll say, but look, you're assuming that all these aftershocks are occurring on planes for which the stress is being calculated, but you don't actually know that, and you're ignoring the fact that we have focal mechanism data. We actually have information on the fault planes that rupture during these earthquakes. Why aren't you using that? So it should be used, but now you bump up against the yin-yang of seismology, which is the focal mechanism gives us two options, the two different possible planes. The shear stress on those two planes is the same, but the normal stress is not, so we have to deal with this ambiguity. Now, some very thoughtful people have figured out a way to get around this problem. Jean Hardebeck and her co-authors said, well, look, let's calculate the Coulomb stress change on both planes, and then we'll take the plane most favorable with the reddest number. And you say, wait a minute, that biases you toward satisfying your hypothesis. That's true, so what we have to do is compare this Coulomb index before and after the earthquake. And that's what you see here for Northridge. The point is that the Coulomb index bumps up by about 20% and stays high for the full 5 years that she examined after Northridge, and the same is seen for Landers. In other words, the actual rupture planes of these aftershocks are consistent with the Coulomb hypothesis. The stress on these planes is tending to increase the shear failure and unclamp the faults. Now, Nano Sieber and John Armbruster approached this in a slightly different way. For Landers, they tried to interpret which are the rupture planes, the real rupture planes, and which are what we call the nodal plane, the plane which is not the one in which the rupture came on. They get more or less the same result, a bump up of 40 or so percent. But what's interesting here, hidden in here, is perhaps a clue of something else, which is the gray ones are the ones which are the opposite planes and which should not be promoted because they don't have the right orientation. And yet you see in the first half a year or so quite a bump up that then comes down below. And that might suggest that something else could also be going on here in addition to the transmission of stress. Now, at this point, you might say, well, you argued to us that we should see aftershocks and we should see antishocks. We should see places where the seismicity rate declined because the stress declined. And when we're looking at focal mechanisms, we get no news about that whatsoever because we can only look at where the aftershocks are occurring. So show us, and I showed you a hint, just a hint, in the Northridge data that in the blue zones we saw a decrease in the rate of seismicity. So how can we really prove that part of the two-part model? So to do that, you have to go to a place where the seismicity rate was very, very high before the earthquake, because only if the rate is high to begin with can you see it drop. Okay, so where do we go in California where the background seismicity rate is high? We go to the creeping section of the San Andreas. It's got the highest rate of earthquakes that we have anywhere. And the Coulomb earthquake actually transmits stress to the San Andreas in 1983. And it turns out that it increases the shear stress on the creeping section and coincidentally decreases it along the Lock Parkfield section. Now what I'm going to do on this plot is superimpose the observed seismicity rate change. Red if the rate increased after Coulomb, and blue if it decreased. And that on a little strip along the fault. I think you can see that these are correlated once again. There's an increased rate of seismicity where we calculate the shear stress to have right lateral shear stress on the fault, and a decreased rate of seismicity in the place where failure would have been inhibited. The data is good enough that we can look at this in cross-section. So here's where the 1966 epicenter is. So we have a decrease in shear stress here and an increase here, and here's what the seismicity rate change looks like during the first year and a half after Coulomb. With time, this phenomena changes. While the increase disappears and fades away, but the decrease remains. And our thinking is that in the creeping section, you subject the fault to stress, and it slips, and it dumps that stress. After that, the seismicity rate goes back to normal. On the other hand, at the block section, the fault cannot slip backwards very easily, and so it can't dump the stress as easily. So let me show you how we make that calculation. And you can see as well that we have another piece of data. We have the creep meters that are recorded here. And notice that at Middle Mountain, right above the 1966 Parkfield zone, the creep meter actually went backwards during the several years after the Coulomb earthquake, and others just stopped moving for several years. So we subject the fault to the stress, which is shown in the color, but we know that this part of the fault is welded shut. It's currently locked. So if we stress the fault with that part locked, this is the kind of slip that we would expect at the surface. So for example, at Middle Mountain, it would want to slip backwards by 22 millimeters. So we impose that 22 millimeters of back slip over the period that we see the fault retarded, and we can match those creep meters. So here, we can not only see that in a region where we calculate the stress to have reversed on the fault slows or reverses, and we can also see this reflected in creep meters. And this permits us to make a probability analysis for this region of great interest, the Parkfield zone. So the renewal part of the probability brings us up to about 55 or so %. These are 10-year probabilities for Parkfield, and the effect of the interaction drops it down. Now you say, wait a minute, the uncertainties have to be much larger than this red line, and that's true. So what I would say instead, speaking from the agency that bet the farm on the Parkfield earthquake occurring in the late 80s and it didn't come, that this period here is an excused absence for the Parkfield earthquake. It's no man's land after this, but I would like to say that we can rest on that part of it. Now at this point, you might say, okay, you've made a case that if you decrease the stress on a fault, you can decrease the rate of creep, but we all know that the creeping section of San Andreas is a rather unique place and not typical. Show us that you can see aseismic creep occurring where you stress a fault toward failure. And a recent example in the literature gives us just such a shot. It's an earthquake in Iran, studied by Barbarian et al. This is an interferogram. It's essentially contours of uplift for an earthquake that was centered here, the Fandoka earthquake. But you can see these interferogram contours extending out to the Shadad thrust. And Barry Parsons and Eric Fielding modeled that as aseismic slip on the Shadad thrust. The agreement of right and left is the suggestion that they've got it right. So why not just put the rupture in here and calculate the stress that the Gok or the Fandoka rupture transfers to the Shadad thrust. And so I'll show you that here. So what happens is most of the Shadad thrust turns red. And you can see that very clearly in cross-section. This is the component of stress we're calculating that's promoting shear and unclamping along this fault. And you can see most of the fault is brought closer to failure, and this fault seems to have slipped aseismically about 8 centimeters. So we're seeing backwards and forwards triggering associated with earthquakes, some of it seismic, some of it aseismic. But at this point, you're going to come back and say, well, look, all of these are one-shot deals in the sense that you've got one earthquake that pushes something forward or one earthquake that pushes something backwards. It would be much more impressive if we had some cases where we could actually see successive earthquakes turning seismicity on and off. So we have the kind of seismic spigot being controlled. And let me show you a case where we do see that. This is the 1997 Kagoshima earthquake in Japan, an earthquake in March that was followed by an earthquake of about the same size along the white lines in May. Now I want you to kind of focus your attention on this lobe and look what happens when the second earthquake occurs. You can see how this had been the place where we had this kind of blowtorch of red and seismicity occurring, but when this earthquake occurs, that turns off. You want to see that again? Okay, so look out here where there's a lot of aftershocks, and now it turns off. And by the same notion, let's look at this site, which is just mildly yellow, has a very small stress increase, but after the second earthquake, it has a very large stress increase and turns on. So here we seem to see these two earthquakes being able to toggle seismicity, and in fact, if we just close in on this box, look at what the earthquake record looks like in that box. It's decaying, we're off the end in one of those red lobes, and the moment the May 13th earthquake occurs, it drops by an order of magnitude, the rate of seismicity on that box. And that second area we looked at, the reverse occurs. The rate of earthquakes in this box increases by an order of magnitude when the stress is changed, again, by just a few bars. So in this one case, we see the ability to turn seismicity on and off. And we can also see this at Landers. I'm starting the clock at the time of the North Palm Springs earthquake. Here, the earthquakes are each is a dot according to its magnitude, and you can get a sense of the background rate of earthquakes. The Joshua Tree earthquake occurs, and we're looking in just this box. And I've put the box here because it's dead in the middle of the Landers stress shadow. And what happens is when the Joshua Tree earthquake occurs here, it turns this area red, and you can see the rate of earthquakes climbs way up. When Landers occurs and this condition obtains, you can see that seismicity drops by at least an order of magnitude. When the Hector Mine earthquake occurs, which is up here, it's in one of the end red lobes again, and it turns it on again. And we can just plot the stress changes that we calculate in that box and see that even a small stress change seems to dramatically turn on the seismicity and be able to turn it off. But there's also a hint of the same thing that I saw or pointed out to you in Nano Sieber's work, which is why don't the earthquakes turn off right away here? There seemed to be some leakage beyond this membrane, as if over the space of about a year, there are still earthquakes occurring where we think the stress should have dropped, which might suggest that there's some other process going on, perhaps related to shaking or the dynamic Coulomb stresses, that might take a little bit longer to quiet out. So at this point, you're going to throw at me your biggest guns. I've tried to make the case that there's a clear association between stress increases and seismicity rate increases, decreased stress decreases and seismicity rate increases. I showed you it's consistent with focal mechanism data, large earthquake occurrence and small. And you're going to say, well, look, you've shown us a half a dozen cases or so, but for all we know, you've looked at 100, and these are the ones that worked. And so aren't these all possibly special cases? Now, that's a vicious thing to say to me. Very much below the belt. But to some extent, we all do this. And so we do need to make sure that what we're doing is not just culling from the vast number of earthquakes that are out there and showing you the ones that work. And Tom Parsons has just completed a study that gets me out of this bind, which is he's gathered up more than 100 magnitude 7 and larger earthquakes from around the globe. Now, in almost all of these cases, it's very easy to tell which of the two nodal planes is the fault plane because most of them are on subduction zones, and we know where the subduction zone is, or large transform San Andreas-like earthquakes, and we know what the fault is. So then he's calculated the stresses produced by each one of these triggering earthquakes and grabbed all the successive earthquakes that are in the Harvard CMP catalog in which the stress is calculated to have changed by 1/10 of a bar or more. And here's where these earthquakes are. They're generally within a couple hundred kilometers of the triggering earthquake. And then he's just tabulated, well, which of those triggered earthquakes are ones in which the shear stress was increased toward failure and which is where it decreased. And what he sees is that we have 60% more subsequent earthquakes where the stress has risen. So this is very good news because there's nothing you can do to tweak this. This is using the entire catalog. But there's still something bothersome here. Why is the blue bar as high as it is? I mean, if the Coulomb hypothesis were the only story, shouldn't it be 0? Shouldn't we never trigger an earthquake in which we've dropped the stress? Now, you can weasel out of this to some extent by saying, since he doesn't know which of the two nodal planes is the plane for this triggered, the second earthquake, he cannot calculate the normal stress change. So maybe some of the earthquakes in the blue bar were unclamped, and he can't check for that. But it's also possible that this is that same phenomena that's kind of hinted to us before of something happening immediately after the earthquake that dies away, in which case we should look at the time behavior. And what the time behavior tells us is that while the stressed earthquakes stay above the background level for about 10 years and are very nicely satisfied by that 1/time decay we've now seen on small earthquakes or large. You saw it collected for all the magnitude 6.7 and larger on the North Anatolia, and here's collected for the whole globe. But the blue has different behavior. Within about a year, it's at the background noise, just similar to what we've seen before. And it suggests that there is another process which we haven't fully gathered, that a number of people, such as Joan Gomberg and Debbie Kilb and Paul Bowden, are working on to try to understand what other triggering mechanisms might be there. But the lion's share of the action seems to be explained by this stress interaction. Now, how do we put this together to provide some kind of realization of what seismicity should do or how it should evolve if this phenomena is correct? And I'd like to, in this closing animation, show you how we do that. And I'm going to go back to where we started, where I burned you on that game. And let's just look at the evolution of seismicity at Landers. Now, in this animation, the color is not stress. What we've done is translated stress into our expectation of seismicity rate using the state and rate friction ideas that I showed you before. And white is a constant rate, and if the warm colors mean we expect the seismicity rate to increase. So we're going to start the clock with a little magnitude 5.2 Galway Lake earthquake, and then it's joined by the Homestead Valley shock. Notice we're building a kind of a ridge of expected high seismicity, and then we come up to the North Palm Springs earthquake, and that's increasing the length of the ridge here. And even though this is fading with time, it keeps being bolstered by the next earthquake to come along, which in this case is the Joshua Tree earthquake. And now this ridge is actually about 70 kilometers long, and then whammo, that ridge gets filled by the Landers earthquake. Now, I've stopped the clock here to show you something really interesting. Nobody had yet looked at what the catalog, the seismic catalog, looked like during the 3.5 hours between the occurrence of Landers but before that Big Bear aftershock that I referred to. The catalog is woefully incomplete for this period, just about magnitude 3 and larger. But what we see is some earthquakes along the fault, a few up here where we're going to see a lot of seismicity subsequently, one here where we eventually get a large earthquake, but look at the cluster here. Now, it looks from this plot as if the expected seismicity rate here and here and here is the same, but I've saturated at a very small increase, 2. If I didn't saturate it, you would see that the expected increase in this first day after Landers is a factor of 70, where the increase here is only a factor of 3. In other words, we're expecting a dramatically higher rate of earthquakes in this zone, and what happens in this zone is the Big Bear earthquake occurs. And then when we plot the aftershocks, or the seismicity which follows this sequence, you can see that it's very consistent with this pattern of a distribution of expected seismicity. And you also see that process fading, and then we have the Hector Mine earthquake. Notice that now the Landers earthquake is actually not a very strong signal anymore. It's faded back, just like its aftershocks have faded back. Big Bear has more punch and is still filled with aftershocks. Now Hector Mine is a much more important magnet for seismicity, and the big increases that we saw on 2 threatening parts of San Andreas are fading. This is the condition for today, and if we run the clock forward out for another 9 years, we can see that Landers' memory slowly fades away. Hector's memory, which is a magnitude 7.1, survives slightly longer, and we end up with a picture that evolves. So to come back to the game we started, in a sense, we're both right. If you played this out for a long enough period of time and averaged it out, the rate would be 1, and your 1 in 30,000 estimate of the probability would be correct. If we played this out for just that first day after Landers and took a 100 by 100 kilometer box here, yes, the probability would be 2/3. But in another sense, we're both wrong because we can do so much better. Even though the probability might be 2/3 in the box, you can see that there are places now and right after Landers where the probability is actually much lower than it was before, and other places where it's considerably higher. So the direction that I would like to point you, and the direction I think that we'd like to head as a community, is to build in what we understand about how seismicity evolves, how these interactions occur, and bring us to a better understanding of earthquake interaction. And now to close, I would like to do something very important, which is acknowledge my animators, Thomas Duez and Rachel Margaret, who both spent a year with us at the USGS. I'd like to acknowledge that the software that was used for almost all these calculations is publicly available and online, as are the animations. And finally, the most important task today is to acknowledge my brilliant and wonderful collaborators, Shinji Toda, who's very embarrassed right now, from Japan. I got to get that fly off his nose. Jim Dietrich, our treasurer at the survey, he's frowning because he had no idea that when he fired that cannon it would cause this landslide. Now watch my collaborators slowly get more undressed. This is Tom Parsons at the USGS. And finally, from Istanbul, Aykut Barka. Thank you very much.